In 1977, humanity embarked on one of its most audacious ventures, launching the Voyager spacecraft into the vastness of space. These twin probes, symbols of our insatiable curiosity, ventured far beyond the familiar planets, aiming to uncover the mysteries of the very edges of our solar system. As we journey with the Voyagers, we bear witness to their incredible odyssey, exploring realms where no probe has ventured before. Their golden records, a testament to the human spirit, carry our greetings to any who might find them in the cosmic ocean. Yet our exploration does not end with the Voyagers. Far beyond the gas giants, in the shadowy fringes of our solar neighborhood, lies Pluto. This distant world, once a planet in our textbooks, now stands as a gateway to the outer solar system. Through the eyes of New Horizons, we have glimpsed its wonders: towering ice mountains, vast nitrogen glaciers, and the enigmatic heart-shaped Tamo Regio. Pluto, in its silent beauty, challenges our understanding and invites us to delve deeper into the unknown. Beyond Pluto, whispers of an unseen world stir the scientific community. This elusive Planet 9, hidden in the darkness, bends the paths of distant objects with its gravitational embrace. Its existence, inferred from the strange orbits of trans-Neptunian objects, hints at a world yet to be seen, a planet at the very boundaries of our solar system. Join us on a journey to the mysteries on the boundaries of the solar system with the Voyager saga, the enigmatic Pluto, and the elusive Planet 9. In the sweltering summer of 1977, a cosmic opportunity loomed on the horizon. The planets of our solar system were aligning in a way that happens only once every 176 years. This rare celestial event opened the way to the unknown and gave us a chance to embark on a great journey to the outer planets. Using this happy coincidence, NASA engineers and scientists conceived of a mission in which two probes would slingshot from planet to planet, using the gravitational pull of each to propel them farther into the depths of space. The technological marvels that were Voyager 1 and Voyager 2 were equipped with the most advanced instruments of their time. From imaging systems capable of capturing Jupiter's swirling storms to magnetometers designed to study Saturn's magnetic fields, these spacecraft were to rewrite our understanding of the solar system. But the journey to the launch pad was fraught with challenges: budgetary constraints, technological hurdles, and the boldness of the mission objectives pushed the team to the limit. Every component of the spacecraft had to be painstakingly tested, every system optimized for the rigors of space. As the launch dates approached, the excitement was palpable. 3, 2, 1. We have ignition. We have liftoff. Soaring into the skies, these twin messengers carried with them the hopes and dreams of all mankind, embarking on a journey that would forever change the way we think about the cosmos. When Voyager 1 and Voyager 2 traveled beyond the asteroid belt, they were greeted by the colossal presence of Jupiter, the gas giant that gravitationally dominates our solar system. These encounters set in motion a series of groundbreaking discoveries that would overturn our view of the outer planets. Armed with a host of sophisticated instruments, the probes peered into the planet's turbulent atmosphere, revealing the dynamic and violent nature of its storms. The imaging science system, a key component of Voyager's arsenal, captured stunning details of the Great Red Spot, a storm larger than Earth itself, and revealed never-before-seen features. But perhaps one of the most unexpected discoveries was the existence of Jupiter's thin ring system, a ghostly band of dust and particles girdling the planet. This discovery, made possible by the ship's photopolarimeter, disproved the notion that rings were a feature exclusive to Saturn. Among Jupiter's moons, Io stood out for its fiery temperament. The observations revealed a world with volcanic activity, the first time such phenomena have been observed outside of Earth. Moreover, Io is the most volcanically active body in our system, its surface forever changing under the inexorable forces of its interior. Images of towering plumes and lava flows have changed our understanding of geologic processes in the solar system. As the Voyagers continued their journey to Saturn, unprecedented beauty awaited them. The complex and intricate structure of Saturn's rings came into view, and the probe's cameras captured the subtle interplay of light and shadow among the countless ice particles. The scientific instruments aboard the spacecraft, especially the radio system, played a crucial role in studying the composition and dynamics of Saturn's rings. The data collected revealed the complex structure of the rings, including the mysterious gaps and braids, phenomena whose formation continues to intrigue scientists to this day. Titan, Saturn's largest moon, was another highlight of the mission. Shrouded in a thick atmosphere, Titan was a world of mystery, its surface hidden from view. However, thanks to the ingenuity of Voyager's instruments, glimpses of this mysterious moon suggested the presence of liquid hydrocarbon lakes and a complex weather system, sparking curiosity and speculation about the possibility of life on it. The Voyager 1 and Voyager 2 encounters with Jupiter and Saturn have not only expanded our knowledge of the hot gas giants, but have also opened new frontiers in the exploration of the outer solar system. In the cold and distant reaches of our solar system, Voyager 2 set out for a solitary encounter with Uranus, the enigmatic ice giant. This historic encounter in January 1986 offered a glimpse of a world that had previously been just a pale blue in Earth-based telescopes. Uranus has presented an enigma to scientists, with its peculiar tilted axis lying almost parallel to the plane of the solar system. This unusual orientation, with poles that alternately bask in the sun and languish in decades of darkness, has a profound effect on the planet's weather and atmospheric dynamics. As Voyager 2 approached, its instruments, including the narrow-angle imaging science system camera, began to capture unprecedented images of Uranus's atmosphere and its suite of moons and rings. The pale blue color of Uranus hid the complex structure of the atmosphere, faint bands of clouds, and previously invisible rings encircling the planet. One of the most striking discoveries was the nature of Uranus's magnetic field, revealed by the spacecraft's magnetometers. Unlike Earth, whose magnetic axis coincides exactly with the axis of rotation, Uranus's magnetic field was found to be significantly displaced and tilted, suggesting a complex and possibly multi-layered internal structure. Leaving Uranus behind, Voyager 2 continued its journey to Neptune, the most distant of the known planets. In August 1989, mankind saw Neptune for the first time up close, a dynamic and turbulent world at the center of which was the Great Dark Spot, a storm the size of the Earth. Neptune's atmosphere, buffeted by supersonic winds, paints a portrait of a planet alive with weather disasters. The spacecraft and its suite of instruments have delved into the mysteries of these winds, capturing the movement of cloud formations and the complex pattern of Neptune's faint rings. Among Neptune's moons, Triton stands out for its retrograde orbit and geologically young surface. Voyager 2 images of Triton showed a frozen landscape dotted with geysers spewing nitrogen gas and dust into space, hinting at a geologically active interior. Voyager 2's encounter with Uranus and Neptune has expanded the frontiers of our knowledge, revealing the diversity and complexity of the outer solar system and raising new questions about the origins and evolution of the planets. As the Voyagers continue their journey into interstellar space, their mission lives on as a testament to human ingenuity, curiosity, and the spirit of exploration. The discoveries made by these intrepid spacecraft have reshaped our understanding of the solar system and our place within it, inspiring future generations to reach for the stars and uncover the mysteries of the cosmos. Through their incredible odyssey, the Voyagers have become ambassadors of humanity, carrying with them a message of peace, hope, and discovery to any who may one day encounter them in the vastness of space. System. This region where the light of the sun is almost unattainable envelopes the planet in total darkness. This remoteness poses a serious problem because the potential position of the planet can encompass vast portions of the sky, requiring extensive focused searches covering these celestial expanses in painstaking detail. It's something akin to trying to find a needle in an astronomical haystack. Moreover, because of its distance from the sun, the planet's surface temperature is extremely low, meaning it emits minimal thermal radiation, making infrared detection just as difficult. The lack of emitted and reflected light is compounded by the glare of distant stars and the myriad cosmic objects that fill the sky, each vying for the attention of our telescopes. Among other difficulties, the nature of the search is compounded by the planet's enormous orbital period, which is thought to be thousands of years. Because the planet's motion across the sky is imperceptibly slow from our earthly perspective, even after a decade, Planet 9's position in space will have changed only slightly, making any attempt to observe its motion in the short term virtually impossible. This chilling rate of motion means that traditional methods of detecting planets by observing their transit or motion against the background of stars are not feasible. However, in the relentless pursuit, astronomers use an array of sophisticated techniques and instruments, from ground-based telescopes equipped with advanced adaptive optics to space-based observatories that circumvent the Earth's atmospheric distortions. So, in the pursuit of Planet 9, astronomers have had to go beyond traditional observational methods, leading to the development of several innovative approaches aimed at refining the elusive planet's location. They utilize unique aspects of the solar system's external environment and potential celestial interactions that Planet may 9 have with other objects. One of the proposed approaches has to do with potential moons that may orbit around Planet 9. Given its considerable mass, it is conceivable that it could have captured one or more moons during its long journey through the solar system. The concept is based on the process of tidal heating, a phenomenon in which the gravitational interaction between a planet and its moon causes internal heat to be released within the moon, potentially making it warmer than the parent planet. This is what allows the satellites Europa and Enceladus to have liquid subsurface oceans, and also provokes vigorous volcanic activity on Io. This internal heating may cause the moons to emit infrared radiation more perceptively than Planet 9 itself, providing an indirect but promising avenue for detection. Another innovative method involves tracking the trajectories of interstellar asteroids passing through our solar system. These high-speed objects, coming from regions outside our solar system, could potentially be affected by the gravitational pull of Planet 9. By meticulously tracking the trajectories of such asteroids, astronomers can infer the presence and location of a planet from the subtle gravitational jolts it exerts on passing bodies. This method was demonstrated by studying the interstellar asteroid Oumuamua, whose path through our solar system may have been slightly altered by such a massive object. The trajectories of spacecraft passing through the outer solar system can also provide valuable insights. Like asteroids, when spacecraft travel vast distances between planets, their trajectories are slightly and subtly influenced by the gravitational forces they encounter. By analyzing the precise tracking data from these missions, scientists can detect unaccounted gravitational anomalies that may hint at the presence of Planet 9. This method requires accumulating huge amounts of data over long periods because the gravitational effects are incredibly subtle. However, the results can be very significant and will pay off in time. Moving from direct observation to indirect detection through a planet's influence on its environment may be the key to unlocking one of the greatest mysteries of our cosmic neighborhood. The search for Planet 9 has also spawned many theories and speculations about the true nature of this elusive object. Among the most intriguing are hypotheses that Planet 9 could be a primordial black hole or a dense dark matter clump, each representing a radical departure from the traditional planetary view. The idea that Planet 9 could be a primordial black hole introduces a sharp twist to the narrative. Unlike stellar black holes formed by the collapse of massive stars, primordial black holes are theorized to have originated in a high-density environment shortly after the Big Bang. These hypothetical entities may be the size of an asteroid, but have the mass of a planet. The possibility that Planet 9 is one of these ancient mysterious objects is compelling for several reasons. First, it would allow us to explain the gravitational effects attributed to it without the need for a visible planetary body. Secondly, this, of course, does not completely contradict the impossibility of its detection, since such an object would theoretically be no larger than a basketball. According to another theory, Planet may 9 be a concentrated blob of dark matter. This form of matter, which does not emit, absorb, or reflect light, accounts for a significant portion of the total mass of the universe, but remains one of the greatest mysteries. Dark matter clumps, theoretical clusters of dark matter, are thought to have arisen from density fluctuations in the early universe. As the universe expanded and cooled, these gravitational fluctuations led to the formation of dark matter structures ranging from small clumps to massive halos surrounding galaxies. If Planet 9 were a dense cluster of dark matter, it could exert the gravitational influence observed in the outer solar system without being directly observable using conventional telescopic techniques. The primordial black hole and dark matter clump hypotheses emphasize the profound implications of the search for Planet 9, far beyond the discovery of a new member of the solar system. Whether it's an ordinary planet, a primordial black hole, or a dark matter clump, one way or another, we'll find ourselves on the favorable side of events. The search for Planet 9 is a testament to humanity's enduring curiosity and relentless pursuit of the unknown. A recent preprint of a research paper by the same Mike Brown and Konstantin Batygin and their colleague Matthew J. Holman, entitled Pan, Stars 1 Search for Planet 9, dated February 1, 2024, reflects the meticulous ongoing efforts to uncover this enigmatic member of our solar system. The study used extensive data from the Pan, Stars 1 survey, which, with its deep and wide sky coverage, provided a unique vantage point for the search. By focusing on single-night transients and using a sophisticated Kalman orbit-linking algorithm, the researchers sifted through billions of detected objects, a task akin to finding a single grain of sand among the entire North American coastline. This methodological approach represents a significant leap forward, building on the foundation laid by previous surveys such as the Zwicky Transient Facility and the Dark Energy Survey. Despite the depth and breadth of the PS1 survey, the elusive ninth planet remained out of sight. No features matching the search parameters were found in the data. This result, while not leading to the discovery of a ninth planet, nevertheless narrowed the search area considerably, excluding 78% of the parameter space in which the planet could potentially reside.